Adding randomness to a program isn't necessarily an easy thing to do. In your favorite language, I'm going to use C++, you most likely have several options. But how do they differ? What is the difference in their so-called distribution? And most importantly, does it really matter? Well, it does, if you want to be precise. A random number is not just a random number. Think about it. With a die, you want to have the same chance for all the values. For another thing, let's say human height, things look different. We have a large number of average-sized people and just a small number of people who are really short or really tall. Let me quickly write a program to generate 100,000 numbers in the range of 1 to 6. Now let's add a visualization of the numbers with their frequency. We are going to plot a histogram. Do you see it? It's more or less flat. In 100,000 rows, each number has been selected about the same number of times. Now, what if I make this one small change? Technically speaking, I'll just switch the distribution. See? Now we have a much higher chance that the program will choose the number 3 and a much lower chance for 6 or 1. What's happening? First off, let's set the stage. Random number generation in programming isn't really random. It's pseudo-random, meaning it uses algorithms to produce sequences that look random but are deterministic. In C++, the random library introduced in C++11 gives us high-quality tools for this. We use engines like MeshNet Twister for generating raw random bits and then distributions to shape those into specific patterns like uniform, normal, or Poisson. Our code uses a seeded MeshNet Twister. This ensures different runs give different results, but you could fix the seed for reproducibility. We do that from time to time. For instance, when you want to have your physics-based simulation looking random, that's real, but it cannot be completely random as it could ruin your automatic testing, such as the ones based on image comparison. To really see these distributions in action, we don't need a graphics library. I'll use a pure text-based system to explain this. And to make the patterns clearer, I'll extend the range from 0 to 100. We are going to work with discrete distributions, but 2, which means we'll be generating integers. To collect and visualize the data, we'll use a single simple data structure, std map, for 2 integers. The logic is simple. For every number we generate, the number becomes the key in our map, and we'll just increment its value, which is the count of how many times it has appeared. We have a template function fillMap that handles this for any distribution type. It loops 100,000 times, generates a value, processes it to an integer between 0 and 100, and increments the count. It's easy. Then we have print histogram, which displays a text-based histogram with asterisks scaled to the max count for visualization. It's relative scaling up to 50 stars, so denser areas stand out. Alright, let's break down several distributions one by one, starting with the uniform integer distribution. This is the simplest. Every integer in a range is equally like. We mentioned rolling a fair die, but here from 0 to 100. More realistically, you can consider D&D and make it 1 to 20. The probability for each value in my case is 1/101. It's great for simulations where you want even chances, like random selection. In code, it looks like that. We have uniform in distribution, uniform in, 0, 100. We fill the map with fillMap, and histogram should show roughly equal bars across 0 to 100, each with 100,000/101, 990 counts. Done. Now Bernoulli distribution. This is a yes, no, true or false thing, like a biased coin flip. Parameter p is the probability of true. Here p equals 0.5 means fair coin, 50% chance of 0 or 1. It's the building block for more complex binomial stuff. In code, we have std Bernoulli distribution for 0.5. That outputs bool, which we treat as 0 or 1. Histogram is just 2 bars, around 50,000 each, at 0 and 1. Everything else is 0 since it can't produce other values. For binomial distribution, imagine repeating a Bernoulli trial n times and counting successes, like flipping a coin 100 times. How many heads? Well, n is 100, p is 0.5, and variance will be 25, standard deviation about 5. It's discrete, peaks at mean, symmetric when p is equal to 0.5. For large n, it approximates normal distribution. In our samples, you'll see values mostly 30 to 70, because extremes are super rare. Probability drops off fast. In code, we have std binomial distribution for integer, and histogram is bell-shaped around 50. Why are the tails so low? Well, to get 100 heads, you need a perfect sequence. Head, 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 head. There's only one combination of frames that achieve this. the probability is 0.5 up to 100, which is astronomically tiny. And well, as you can see, it didn't happen once in our case of 100,000 samples of 100 flip coins. The same is true for 0 heads, just tail, tail, tail after tail. Only one combination gives this result. So why is the peak so high? To get 50 heads, there isn't just one way. You could get head, tail, or head, tail, tail, or tail, tail, head. The number of different combinations that result in exactly 50 heads and 50 tails is enormous. The official formula gives 100, choose 50, which is a number with 29 digits. Since each individual combination has the same tiny probability of occurring, the outcome with the most combinations, like 50 heads, becomes the most probable overall. Another is Poisson distribution. This models rare events over time or space, like close to a whole line per hour. Parameter lambda, equal 20 here, is both mean and variance. It's skewed right for smaller lambda, more likely low count, long tail for higher. With a mean of 20 calls per hour, the standard deviation is approximately 4.5 calls per hour, which represents the typical fluctuation around that average. Standard Poisson distribution for 20. Histogram starts low at 0, peaks around 20, and tails off. It's shifted left because mean is 20, not 50 like others. We could bump lambda to 50 for centering, but this shows the skew. We can model time between events in Poisson process. This is called exponential distribution. For parameter lambda, rate 0.02 here, we have mean 1/lambda, which is 50. Remember, waiting time doesn't depend on how long you waited. In code, we have STD exponential distribution, double in this case. And histogram, well, it peaks near 0, decays exponentially to higher values, up to 100 plus, but climbed. To put it into perspective, Poisson asks, how many events happen in a set amount of time? How many atoms in this sample will decay in the next hour? Exponential asks, what is the time until the next event? We are watching one specific atom. How long do we have to wait until it decays? Let's say the rate, lambda, of decay is 0.02 decays per minute. This means the average waiting time until decay, the mean, is about 50 minutes. Why does it peak near 0? Because in a thoroughly random memoryless system, the most likely thing to happen is for the event to happen right now. What's the probability the atom decays in the first minute? It's, for example, 2%. What's the probability it survives the first minute and decays in the second? That's 98% times 2%, which is 1.96. What's the probability it survives the first 2 minutes and decays in the third? 98 times 98 times 2. You can see that the probability is highest for a short wait, 0 to 1 minute, and it decays from there. The graph is ski slope, starting at its highest point, near 0. Mean of 50 is just the average of all these waits. The huge number of very short waits, 1 to 5 minutes, are being averaged with a few rare very long waits, like 200, 300, 400 minutes, to land the average of 50. The atom must decay eventually, but for it to decay at a later minute, like minute 3, it must first survive all the earlier minutes, minute 1 and minute 2. Since the probability of surviving any single minute is 0.98, the total probability is a multiplication, which gets smaller with every step. Finally, let's conclude with the normal distribution, the famous bell curve or Gaussian distribution. This is the most common distribution in nature, and it's perfect for modeling human traits like height, blood pressure, or in our case, scores from a clinical personality inventory. In psychology and medicine, it is very common to standardize test results into t-scores to make them easy to compare. By definition, t-scores are scaled to follow a normal distribution with a mean of 50 and a standard deviation of 10. The distribution is continuous and symmetric. The standard deviation, sigma equal to 10 in this case, gives us a ruler to understand the data. Thanks to the 68, 95, 99.7, we can say 68% of people have a t-score within 1 sigma of the mean between 40 and 60. 95% of people have t-score within 2 sigmas of the mean between 30 and 70. And 99.7% of people have a t-score within 3 sigmas of the mean between 20 and 80. This shows that the score of 80, the standard deviation above the average, or 20 is so incredibly rare, the tails of the bell curve are tiny. In code, we have STD, normal distribution for double. There is no normal distribution for integer because the distribution itself is continuous. For a histogram, you would see a perfect symmetric bell curve centered right at 50. The vast majority of the samples would naturally fall between 30 and 70, just as the 95% rule predicts. And that's it for today. As you saw, adding randomness to your program isn't difficult, but figuring out which random number distribution is the correct one can be. The hidden trap is that if you only care about one or two numbers, your choice almost doesn't matter. But if you let your program run for a long time or generate many numbers, you must ensure that the distribution you choose for your event is the correct one. Thanks for watching. If you like what you saw and want to see more in the future, hit the subscribe button. See you next time.